Welcome back to The Deep Dive, the show built to give you the shortcut to being truly well-informed. You brought the sources, the articles, the research, the dense white papers, and today we are tackling a mathematical equation that is, you could argue, the central nervous system of modern large language models.
It really is.
Our mission is absolutely laser-focused. We are diving into the complex mechanics of how LLMs truly understand context. Specifically, we're dissecting the attention mechanism after a technique called rotational positional embedding, or, RoPE, is applied.
And this is where we stop talking about LLMs as these sort of magic boxes and really start understanding the mechanical genius that allows them to process sequences.
Right.
For you, the listener, the context is vital. Attention is calculated by pairing up every token in a sequence. So the query token wants to know how much to pay attention to every other key token. That relevance score is fundamentally calculated through a mathematical dot product.
Between the query vector, QMPUM, and the key vector, KOAN. And when you apply RoPE, you rotate these vectors before they are multiplied. This rotation is engineered, well, perfectly, so that the resulting dot product, that attention score, inherently incorporates positional information.
Yes.
So we aren't just looking at the math, we're looking at the design philosophy that lets an LLM know without explicitly counting whether one word is 10 spaces away or, say, 5,000 spaces away.
That's absolutely right. The raw math can look, well, terrifying. It involves some sines and cosines, but what we're going to do is translate that mathematical elegance into functional logic. Our goal is to reverse engineer this formula, piece by piece.
Okay, let's unpack this. Let's start with the fundamental structure. When we look at the RoPE adjusted dot product, that QML.EMAN, the first thing that jumps out is the summation symbol. Sigma from I equals 0 to D over 2 minus 1.
Right. And that immediately tells you something really fundamental about how these enormous high-dimensional vectors are being processed.
It's a computational strategy.
It's a brilliant one. So ILUB represents the total dimension of your vector, the size of the internal representation of a single token. In production models like Elana might be 128, 256, or even higher.
And RoPE doesn't try to calculate the attention score across that long string of numbers all at once.
No, it doesn't. Instead, it divides and conquers.
Divides and conquers.
Yeah,
I like that.
Exactly. The D over 2 part indicates that the entire vector is split into pairs. So if D is 128, you get 64 independent pairs.
Okay.
The summation loop from I equals 0 up to D over 2 minus 1 just tells the processor, calculate the contribution of pair 0, then pair 1, all the way up to pair 63, and then simply add all those results together.
So the model isn't performing one massive, potentially really difficult calculation. It's efficiently processing many small two-dimensional rotations and dot products all at the same time.
You can think of it like a specialized team of 64 mini calculators,
each handling its own unique slice of the vector. Okay, so that gives us the structural foundation. It's a sum of paired contributions. But now, the real question is, what is happening inside that calculation for each pair?
Right. Inside that summation, we see the heart of the rotation logic. If we just ignore the cross terms for a moment, the ones that involve the sign functions, which are needed for the full proof, we can focus on the two main components.
The ones that provide the primary kind of aligned contribution to the score.
Exactly. For any given pair I, the calculation involves, well, a first component, where we take the first number of the query pair and multiply it by the first number of the key pair.
Okay, a simple multiplication.
A simple multiplication that is then scaled by a cosine function. Then, right after that, is the second component, the second number of the query pair multiplied by the second number of the key pair.
So we take both numbers in the pair, multiply them by their corresponding partners, and then...
And here is the key functional detail. Both of those multiplications, the first component and the second, are scaled by the exact same cosine term. And this term is where all the positional information lives.
Okay, here's where it gets really interesting. And this is the core insight of RoPE that you really need to lock onto. When you look at that scaling term, the cosine function, what determines its value is not the absolute position of the query token, M, or the key token, N.
Yeah.
It depends only on the relative position, M minus N.
That is the defining engineering principle right there. The LLM doesn't have to learn through, massive amounts of data that position 10 is different from position 1000.
It just needs to know the distance.
Exactly. It only needs to learn that a separation of 10 positions is different from a separation of 50. It's inherently distance-aware, not location-aware.
That makes perfect sense for efficiency. But let me throw a wrench in the works here. If RoPE focuses purely on the relative distance, M minus N, How does the model handle crucial semantic differences? For example, in the dog bit the man, the token distance between dog and man is 3.
Right.
In the man bit the dog, the distance is also 3. If RoPE only cares about m minus n, does it lose the semantic context, to understand who is doing the biting?
That's a great question, and it really speaks to the fact that RoPE is only one part of the whole transformer equation. RoPE is not responsible for semantic content.
Ah, I see.
The vector itself, the QM and N, already carries all the semantic information. QM is the query for dog, and NaN is the key for man, and they contain all the linguistic features of those tokens.
So RoPE just modulates that.
It just modulates the attention based on distance. In both your examples, the raw semantic connection is still high because dogs and men are relevant to each other. RoPE just enhances or diminishes that final score based on how close they are.
It's a positional filter applied to semantic content.
That's a perfect way of putting it.
That distinction is crucial. It's a distance adjustment, not a meaning adjustment. Okay, so we know the dot product is adjusted by a cosine term based on the relative distance. But what controls how much that adjustment affects the score? That's where the real finesse comes in, which brings us to the rotation angle, theta I.
Exactly. The angle theta I essentially acts as the control dial for how quickly the rotational adjustment cycles through its possible values. And the formula for this angle for a specific pair I at position M is theta I of M equals M times 2 pi over a big theta I.
Where that magic scaling factor is big theta I equals 10,000 raised to the power of 2i over d.
That's the one.
That scaling factor. That's the engineering secret, isn't it? It means every single one of those 64 pairs we talked about is running at a different speed.
Precisely. This is the variable frequency mechanism. As the index I goes from 0, the first pair, up to d over 2 minus 1, the last pair, the rotation speed is deliberately varied.
And counterintuitively, the pairs with the low indices rotate much faster.
Much faster. And the pairs with high indices rotate much, much slower.
If we connect this to the bigger picture, you can think of the entire vector dimension like a high-end graphic equalizer, maybe.
That's a fantastic analogy.
Yeah.
The low index pairs, where E is near 0, are like the high-frequency treble notes. They capture rapid, sharp changes, highly sensitive to positions that are only 1 or 2 tokens apart. They represent short-range context.
And the high-index pairs?
Those are the low-frequency bass notes.
Hmm.
They maintain their presence or their phase over thousands of tokens. They ensure the model doesn't just forget the positional relationship between very distant tokens.
The source material we looked at gives some staggering concrete examples of this, using a common LLM dimension like d equals 128. Let's just revisit those numbers to really appreciate the scale.
Sure. We can look at the fastest rotating pair, the one with the lowest index, I equals 0.
Okay.
If I is 0, the scaling factor, that big theta sub 0, is calculated as 10,000 to the power of 0, which is just 1.
So if big theta is 1, the angle changes by 2 pi radians for every single token step.
Correct. That's one full 360-degree turn per token. This pair is spinning incredibly fast. It resets its positional information constantly. It's hypersensitive to immediate adjacency.
Now let's jump all the way to the other end of the spectrum. The pair with the highest index, I equals 63, assuming d is 128, that's the deepest, slowest part of the vector.
Right. In that case, I is 63. Big theta sub 63 is 10,000 to the power of 126 over 128.
Which is almost 10,000 to the power of 1.
Almost. It approximates to about 6309.6. And that means the rotational adjustment for that specific vector pair is incredibly slow. The angle changes by only a fraction of a degree per token.
I find this absolutely fascinating. A full 360-degree rotation for that pair only completes after roughly 6,310 tokens have passed. That is an incredible range.
It is.
You have one part of the vector resetting every single token, and another part that takes a context window the size of a short novel just to cycle once.
That difference is exactly why RoPE is so powerful for context. It ensures that the model is simultaneously capturing short-range dependencies, like matching verb tense across a short phrase using those fast rotating components.
While the slow-moving, high-index components maintain coherence and positional awareness across thousands of tokens.
Capturing those long-range dependencies, yes.
This just isn't just theoretical math. This is a direct, measurable limitation, or maybe an advantage for models like Llama, which really pioneered the use of RoPE.
It is.
If the slowest part of the vector takes over 6,000 tokens to complete a full positional cycle, That suggests 6,000 tokens is a sort of fundamental horizon for the unique positional information encoded by this specific choice of the base value, 10,000.
That's a very sharp deduction. When Llama was designed, its original effective context window was, around 2048 to 4096 tokens.
Right.
The frequency spectrum encoded by that theta I guarantees that every dimension is providing highly unique positional information up to and beyond those limits. But you hit the crux of the matter. If you push the context window to 10,000 or 50,000 tokens, which is the current trend, those slowest vector components start providing repetitive, non-unique positional information.
Because they've completed a full cycle and are just repeating their pattern.
They're just repeating their pattern.
Which means the model has to rely on other, maybe less robust mechanisms to distinguish between a token at position 6,500 and one at, say, 12,810, because that long-distance RoPE component is essentially recycling its coordinates.
Precisely. It turns that vector dimension into a set of specialized sensors, each tuned to a different distance scale. But that spectrum has a hard limit dictated by the design choices, namely that base number 10,000.
So what does this all mean? We started with a dense, intimidating mathematical formula for the RoPE adjusted dot product, and we broke down its operational principles into, I think, 3 functional takeaways for you, the listener.
I think so. First, the calculation is performed using paired vector components, which breaks a massive task into hundreds of tiny, efficient calculations.
Okay, that's one.
Second, the position is encoded exclusively by the relative distance m minus n via that cosine adjustment. It cares about separation, not location.
And finally, and I think most elegantly, we discovered the key design choice. The rotational speed is not uniform. RoPE's genius lies in its ability to inject this relative positional information directly into the attention mechanism using a massive spectrum of frequencies.
And this spectrum goes from a rapid 360-degree change per token, which is sensitive to immediate neighbors, all the way to changes that take over 6,000 tokens for a full cycle, capturing these vast long-range dependencies simultaneously across the entire vector dimension.
It's an unbelievably elegant piece of engineering that turns a purely mathematical formula into the backbone of contextual understanding for modern AI. Now, here's a final provocative thought for you to consider as you reflect on this deep dive. If the maximum speed and effective range of positional encoding is determined by that base value, 10,000, and we saw the limitations that pop up around 6,000 tokens, what happens if engineers scale that base value much higher? Would a base of, say, 10 billion extend the model's native rotational coherence to context lengths we can barely imagine today? Or would it just make the short-range frequency bands too slow to be useful? That's something to chew on.